Okay, how are you? I want to continue from where we left, looking at pairing. And last time we had looked at Weil pairing, and of course, we will revisit the same thing so that we understand it, the Weil pairing, how it's done, and then how to write the code for it. We had done most of these things, so just revisiting to see, to fully understand it. Now, we recall from what pairing is. Pairing, supposing you have a group, no, supposing you have some elliptic curve. Let me say you have the elliptic curve. Let's call it E. Can use this example, 8, 8. Can use this example. Mod 13. The field is F13. Of course, you know this elliptic curve is just y square is x cubed plus 8x, then plus 8. So you're doing it. Now, this elliptic curve has 20 elements. Of course, the element, no, the points has 20 points. And the points which lie on it, the points which lie on it are just 19. Then plus the point at infinity. So those makes 20. So the point at infinity, as we've always said, this then becomes the identity of the group. So the group has 20 points. The group has 20 points. Now, but if you want to do pairing, you don't do on this elliptic curve on this field. You don't do it on this field. So what you then do, you come up with an extension of this field. So it's on the extension of this field that you then do pairing, not on the original field. So I think that is good to emphasize, so that going forward again, we know what we are doing. We are not doing on the original. The elliptic curve is the same. The elliptic curve is just the same, but now we just extended the field. So to extend the field, first of all, once you notice that it has 20 points, we were coming up with the divisors, the primary divisors of 20, and the primary divisors of 20, 2 go there, 10, 2 go here, 5, and 5 will go here, 1. So the primary divisors of 20 are 2 and 5. Now we pick the largest of them all. The largest of the prime divisors is 5. Now, we then find the embedding degree. Embedding degree. Embedding degree will then be a smaller value k, that will make 13 raised to k minus 1 be divisible by 5. So a smaller value k that will make this be divisible by 5. 5 is this 5. Now, therefore, when you do this, you would find that this k will be 4. So that 5 can divide 13 raised to 4 minus 1. Let me just check what 13 raised to 4 is, and then subtract 1 and see whether 5 can divide that. Thirteen raised to 4 is 28,561. When I subtract 1, I have 28,560. This is 28,560. So 5 can now divide that. So k becomes then our embedding degree. With this embedding degree, we can now extend our field. We can extend our field. It's on this extended field that we can now perform pairing, not on the original field. So now we can extend this. The original field was F13, but this can be extended to F13 raised to 4. So now this field has more points than this. This one had only 20, but this will have more than 20 points. Now, the points of this field, those points, they also form a group. They form a group. But what we want is not the entire group. What we want is not the entire group. We want a subgroup of this group. A subgroup of this group, which we shall call full 5 torsion group. A full 5 torsion group is what we want. So this one has several elements, has more points than this, but we are not interested in all of them. Because of security, we just want a section of this, and a section of these points, the 5 torsion. The 5 torsion, these are points of this group. There are points of this group that have the property that if added 5 times, you would get the identity. If added 5 times, you would get the identity. Those are the points we want. Those are the points we want. We call them the 5 torsion points, 5 torsion points. Now, we are now ready to do Weil pairing. We are now ready to do Weil pairing. We get all these points that have this property. Now, just pick 2 points now out of this. Pick 2 points out of this. How many would they be? There'll be several. There'll be 5, not 5. There'll be several points. There'll be several points. The full 5 torsion points. Okay, we will not pick 2 points from this. After you've obtained this, after you obtain these points will form a group also. The full 5 torsion points would form a group. I want to come up with the 2 subgroups of this. Call one G1 and call another G2. So I'm just recalling what we've just been doing, Look at where we began. We began with this elliptic curve defined on this field. The field has 20 points. We know we will not work with this field. We will then extend it. We'll extend it to have more points. Some of these points will now be a polynomial form. They will be of the form A plus BT polynomial. And of course, this increases our security. We are making it a bit complicated for an attacker, supposing we were to want to encrypt or decrypt, making it a bit complicated. So we now have points of this form. Here, we have points of this form. X value written in this form, and Y value again in this form. So there could be more points, but we are not interested in all of them. What we're interested is part of these points that would satisfy this property. 5P is a point at infinity. Now, so we've attained all the full 5 torsion, but again, we are not interested in all of them. We're just interested with the 2 groups. We come up with the 2 groups of this, 2 subgroups of this. The first subgroup of this, we shall call it G1. And what is this G1? G1 is the 5 torsion group. 5 torsion group. Remember, this was full 5 torsion group, and this is just 5 torsion group. 5 torsion group. Now, 5 torsion group is, these are points, this is a group formed of points that obey the property 5p is infinity, is a point at infinity, but it's defined on F3. You remember this F, remember this extension has points, some of the points are coming from here, the 20 points. Some of these 20 points are here. Some of these 20 points are here, and we have additional points other than the 20 points that we got previously. We have other points. So the 5p, the 5 torsion groups, would then be part of the 20 which are here, part of the 20 which are here that obey this property, part of those 20. These ones will just be 5, will just be 5 points. But these ones are not 5, these ones are more. These ones are more. These ones are not 5. Full 5 torsion points are more. Full 5 torsion points are those which obey this property and are here, are part of this. So you know, part of this, we have those which are in polynomial form. So part of even those which are in polynomial form and obey this property are points of 5, full 5 torsion. When we talk of the just 5 torsion, just referring to 5 points from this field, 5 points of the elliptic curve defined on this field, the original field. Of course, they are also here. So there will be 5 of them. So this is what we call group 1. Then group 2 would comprise of points of this full 5 torsion group that obey the property that x raised to p, y raised to p will be the same as 5p. Be the same as 5p, where the first p here and p here is 13. In our case, is 13. The mod is 13 in our case. But this other p here is the point. So supposing the point P is xy. Supposing point P is xy. Capital P, point P is xy. Then, and supposing our mod is 13, what I'm talking about is that points that we shall call group 2 will be points of this full 5 torsion that obey the property x raised to 13, y raised to 13 will be the same as xy. This point P, let me just call it P, added 5 times. Added 5 times. So we call those ones. All those points that obey will fulfill this property. All those of the all of them that will fulfill this property, we shall call them group 2, G2. Now, so we now have group G1, we have group G2. We are ready to do Weil pairing, because you must have those 2 groups to do Weil pairing. Now, so what does it say, therefore? What does Weil pairing say? Or what does just pairing say? Pairing says that you pick 2 points. Pick 1 point from the group 1, pick another point from group 2. Coincidentally, some of the points in group 1 and group 2 will be the same. Coincidentally, some of the points here and points here will be the same. But we're just saying pick 1 point from this group, another 1 point from this group, and then the pairing will be the map. that maps, let me say, point P and Q, where P is coming from maybe the first group and Q is coming from the second group, such that if there is an integer multiplied by that, another integer multiplied by that, it will give you the same result as P Q then raised to AB. So this is what pairing will be doing. So just picking a point from this, another point from this, then you do this map. So this map will then pick, for instance, if there is a constant multiplied by A and then another constant multiplied by Q, the result will be this. So that is then what we call Weil pairing. But you can see where it come from. We began with an elliptic curve, and this elliptic curve is defined on some field. And this field we are not working with. We do its extension. We do its extension, and that's where it came from. We did that extension earlier. So the extension gives you is now another field, and now more points. That is why we are extending, that we can now have more points to work with. Of course, we do not want an adversary, for instance, to know the points we are working with. An adversary may get to know the group, may get to know, for instance, the elliptic curve. An adversary may get to know the field we are working with. But now the points are the ones we are trying to play with, so that nobody can easily tell the point you chose. So after you've extended the field, come up with embedding degree. After sometimes the embedding, we have the divisors will be many, and so conventionally, you would then choose the highest divisor that will then assist to come up with embedding degree. And then after that, you extend the field, and of course now get a full R torsion, where R is the divisor. For instance, our case, full 5 torsion. Now, after obtaining this full R torsion, you would then get this subgroup. This, of course, is a subgroup of this, G1, and G2 is a subgroup of this. And this is just, to get this, we do it on the original field. If the field is F13 but the original field here was F13. So then using this original field, getting elements that when modular, because R elements which multiplied by R will give you the point at infinity. In our case, our R is 5. In our case, our R is 5. So we're getting elements which, when added 5 times, give you a point at infinity. And then we'll also get G2. G2 said we're getting elements which, supposing this is our element P, X, Y, we're getting elements which, when X is raised to the mod, in our case 13, and Y is also raised to 13, you would get this result as 5P. So all those points that fulfill this condition are part of this group. We will not use all of them. We will not use all of them. We know that if R is 5, we will have only 5 points. And R is 5 here, again, we'll have 5 points. So this group has 5 points. This group has 5 points. It's a subgroup. A subgroup, of course, is a group. That's why I'm referring to it as a group. So this one has 5 points. This one has 5. We only require 1 point from this and 1 point from this. Out of those 5, we only require 1 point from this and 1 point from this. Then we use them to do Weil pairing. And again, another point we've emphasized that Weil pairing, we've seen so many forms of elliptic curves that Weil pairing will be done on Weierstrass, short Weierstrass form, not just any other form, but the short Weierstrass form. So if you have your elliptic curve in some forms like, let me say, Montgomery, you would want to, or Edwards, or twisted Edwards, because we have so many forms, you may want to, first of all, convert it to Weierstrass. And that is why at some point, we were learning how to convert from one form to the other form, because there are forms that would enable some computation on them. Like the short Weierstrass would enable Weil pairing. Montgomery form would enable something different. The short twist, the twisted Edwards would again also enable something different. So that is why it was important for us at some point to know how to convert from one form to the other. Now, so once you have those 2 points, P and Q, then you compute Weil pairing in this manner, are then calculated. These ones are calculated by Miller's algorithm. You cannot do them physically. It will take you very long. You compute this. These are just the elements. They are elements of this extension field. They are elements of the extension field F13.4 in our case. So they would then be computed by the Miller's algorithm. So that means you're writing your code, and then you must have this part for computing FRPQ and FRQP. The Miller's algorithm, that part must be there. Now, so what other part do we require for doing our code? So we've already seen that we will have a function for doing Miller's algorithm. Of course, we will then require another function for doing Weil pairing. So, of course, after you've computed this and that using Miller's algorithm, then Weil pairing would just be computed by this formula. So then you have a function for doing that. These are not the only functions we require. We also require the main function, but even before we reach there, we would require a function that will be giving us summation or doubling of points and summation of points. This Miller's algorithm is computing this by successive doubling of points, So that means if we have point P, it will be added P plus P to get it to P. And then again, about 2P plus P gives you 3P. So that is what Miller's algorithm will be doing to get these points. So doing successive doubling. So that means you require a function for doing summation. And in our codes, we've always had this. In our codes for this, we've always had this. So you're giving your code the formulas for getting slope. For instance, you're telling it if these 2 points are different, of course, 2P and P will be different. You're telling it, you then get the slope as y2 minus y1 over x2 minus x1. Then, of course, at this point, you're telling it, it cannot divide this one like this. You cannot divide it like this. So you would have some point for getting the inverse of denominator. The inverse of the denominator. So you must have a function for doing the inverses. Function for doing the inverses. So that this lambda can now be written as y2 minus y1 multiplied by the inverse of the denominator. Inverse of the denominator, x2 minus x1. So you have this function for doing the inverse. Then when you reach here, you are telling your function for doing this summation that instead of doing this, you would then be doing this. Of course, this one can never be done by a code directly. So it's doing it this way. Now, after it has done this as lambda, our slope, we're telling it then, how do you get x3? You're telling it x3 would then be lambda square minus x1 minus x2. In cases where the point is the same, instead of this, where the x1 and x2 is the same, you're telling it to be lambda square minus 2x1. Where x1 and x2 are the same, you're telling that x3 will be obtained this way. What about y3? You're telling it that y3 will be lambda into x1 minus x3, then minus y1, where x3 has been obtained. So you're giving it all these formulas. And you're telling it where you're doubling like this, you're doubling like this. How do you get gradient? You're telling it that gradient will be 3x1 square plus a out of 2y. 2y1. So you're giving it this formula again for getting gradient in cases where P and P are the same. And then after getting that, after getting lambda, you are telling it now get x3 like this, get x3 like that, and get y3 like this. So for getting x3 and y3, the only different part is how do you get gradient when the point is the same or when the points are different. So these are part of the functions we require in our code. And what you notice is that this function for doing inverses, we already have it. We've been doing it. So it will be the same thing. And then the function for main function, this one it will be calling on Weil pairing, and of course you're also giving it the points, giving it P and Q. So the only new thing is this, the function for the Miller's algorithm, and then the function for the Weil, for doing Weil pairing. Those are the only new things there. But the rest will be the same. The rest will be the same. We've looked at them before. Now, so it will be interesting for us again to look at the code, how the code looks like, and then we see how to, if we can customize it or try to improve it to do more things for us. But basically, that's what we require. So now, I've stated why Weil pairing is important, cryptography. And I've also stated why it's possible to do Weil pairing. I've said it's possible to do this Weil pairing because it will allow us to do computations on exponents by splitting the exponents. So when you split the exponents, then you are able to do that just is a way of trying to speed up, is a way of trying to speed up computation. It's just a way of trying to speed up computation so that if you have something like 5 raised to, may say 4, and 4 is a big number. I'm just using this as an example, and I want to compute. It's easier if I was to speed it by having, for instance, do this and then do this, then combine the results. That's what I mean. I say by it allows computations in the exponent to be split into different parts. And then these different parts will then be computed differently, and the results are put together. So for instance, if I wanted this computation, if I know it will take me long, it's easier for me to, first of all, just split, and I have 5 raised to 2, 5 raised to 2. Somebody else can do for me the 25, and another person could do for me 25. Then I will just merge the 2 results as 25 times 25 and get 625. So it will be the same result, but you can find that if this number is huge, then this doing this directly will then involve a lot of computation. But then to easen that, you can split, and that will easen the computations. So that is why it's very important. It's very important, and that is why it works. Now, so again, another point we mentioned last time is that Weil pairing is not done on every elliptic curve. It's not done on every elliptic curve. The elliptic curve that we can perform Weil pairing, it should be pairing friendly. Should be pairing friendly. Now, so the question is, what are pairing friendly elliptic curves? So these are elliptic curves, and I'll show you. I'll show you some of the properties that they should have. But pairing friendly elliptic curves, as the name suggests, these are elliptic curves on which we can do Weil pairing. And the thing is that they must have a prime factor R, and this prime factor R should be one that can allow efficient computation of Weil pairing with respect to R. The prime factor here, I said, for instance, 20. I said, for instance, if the group has 20 points, the prime divisors of 20 are 2 and 5. So you're saying that Weil pairing, the pairing friendly elliptic curves must have an R. This is our R. And this, of course, I said in this case, we have several divisors with picking the largest of them all. But this R should be one that can allow efficient computation of Weil pairing. And I'll repeat the example we looked at last time. The example we looked at last time was one of the elliptic curve 1, 1, mod 5. Mod 5. We discovered that our R here is 3. And since R is 3, when you are computing this Weil pairing, the denominator happens to become 0 when you calculate this using Miller's algorithm. The denominator becomes 0. And so when the denominator is 0, it means that this result is not there. You cannot do this. You cannot do this. You cannot divide by 0 because the denominator is now 0. So this division cannot. So this is an example of an R that is not allowing efficient computation of the Weil pairing. This is just an example of an R that is not allowed for Weil pairing. So we're saying that R must be one that allows efficient computation of the Weil pairing. So how should R look like, therefore? How should R look like? We've already disqualified R like, we've already disqualified 3. 3 cannot be R. So how should R look like? Remember that R is the one that is assisting us get our embedding degree. And remember that our embedding degree is supposed to be one of these. It's either 2 or 4 or 6 or 8. So our embedding degree is supposed to be this, one of these. So this is just a reminder of embedding degree and how it's computed. The R must be, so embedding degree must be smallest integer, positive integer, that allows this to be divisible by R. And our R, we said, shall always be the largest of them all if we had several. If we had several, the largest of them all. So our R is supposed to be greater than 3. Our R is supposed to be greater than 3, not 3 and less. So if it's 3 and less, then it's not possible because the denominator will then become 0. And therefore, we will then not be in a position to find that quotient, not be able to do that. Now, but we already have, in practice, we already have a pairing-friendly elliptic curves that some companies use for some reasons, and therefore it's good to also adopt them when you are doing Weil pairing. For instance, the most popular one, of course there are several, but I've just here listed the most popular, BN254. BN254 is an elliptic curve of this form, where B here depends on the company that is using it. So the company would vary the B. But what remains common is that this elliptic curve does not have a value. You cannot see a value. There's no AX. There's no AX. So just X cubed plus B. And the mode, our characteristic P here is 254 bits. So this is a very big number. 254 bits is a very big prime number. It's a very long prime number. So this elliptic curve is called BN254, where the 254 are the bits, 254 bits. The embedding degree for this elliptic curve will then be 12. And this one is commonly used in Ethereum ZK snarks. It's also used in Growth 16 and long algorithms. So I said every company would then have its own pairing-friendly elliptic curves. Every company has it. There are so many. I've just listed the most popular ones. Now, this one, if you're writing the Rust code for this, then you would require to import these libraries. These 2 libraries would then be crucial. Of course, you may require more other libraries that would assist you, but these ones are a must. These 2 libraries are a must if you are doing this. The other commonly used elliptic curve is the BLS 12381. It's of this form. This also lacks the AX, But the difference with this from the above was 254 bits. The characteristic was 254 bits. But this one, the characteristic is approximately 381. More than 256, more than 254, more than 254. It's a very long prime number. 381 bits is approximately this, 381 bits. So this is what makes it different from the above. At this one, you can see the B has been defined. The B has been defined as 4. The other one, the B was not defined so that every company will then put its own B. Every company will then put its own B. Where is it used? It's used by Ethereum, BLS signatures, and ZK snarks. And for you to implement this, then the libraries, you must add these libraries to elliptic curve. To your code, must import these libraries. So these are the most commonly the most popular elliptic curves. Now, the reasons that are used, again, I've included them here. The reasons that are used or why they are recommended. And of course, most of the reason is just security. Looking at elliptic curve that will give us a security and so on. Now, just before we look at the code, I want us to do some calculations that will assist us then be able to write, for example, how the code will be doing inverses, how the code will be doing point addition, how the code will be doing doubling, and so on. So this calculation is just meant to assist us to know how to write the code. Now, so the example is, consider the elliptic curve is defined over this. This is an extension. Of course, we talked of F13, but we said because we want to do pairing, then extend it, and the embedding degree was 4. So we extend it to this field. So then when you're extending that, you must then define an irreducible polynomial that will be assisting us to reduce whenever we're doing multiplication and the result goes beyond power 4. The result goes beyond power 4, we need to reduce it using this polynomial. So that the result is always supposed to be less than power 4. It's supposed to be 0 or 1 or 2 or 3, but not 4 and above. So if it's 4 and above, and then we have to reduce it. That is the power of the polynomial. So for instance, T4 would then equate to 0. This one equates this to 0. To be 2, 4 is -2. So that means every time you're multiplying and the result of the polynomial is power 4, you reduce it. You make, so for example, if you get 3T4, after your multiplication, if you get 3T4, then this should be the same as 3 multiplied by -2. T4 becomes -2. Or if you don't want to get -2, you don't want to use -2, since you're doing it mod 13, -2 mod 13 is 11. So you would either write it this way, or you write it as 3 multiplied by 11. These two are the same. Because this is 6 negative, -6 mod 13 is the same as 7. The same as 7 because -6 plus 13, -6 plus 13 is 7. What about this? This is 33, but you're doing it mod 13. Mod 13. So What is this? Okay, okay, this part was -6. Mod 13, that would be 7. I think I'm correct. 7 plus 6 is 13. What about this other part? This will be 33. And mod 13, what will that be? So 13 goes here twice because of 26. Subtract 26 from this, you have 7 again. So you can see these two are the same. So you're either reducing it by replacing t raised to 4. T raised to 4, you replace it by -2, or you can replace it by 3. What about if you have t raised to 5? Supposing you multiply and got 7 t raised to 5. So t raised to 5 will be the same as t raised to 4 times t. So that means this will be the same as 5 -2t, which is -14t. And this negative, so when you make it positive, the answer here will be 12t. Just -14 plus 13, this gives -1, then again add 13, that gives you 12. So you add until you get a positive number. This is one way, or you can use 11. So it will be 7 times 11t. Instead of -2, you can use 11. This will be 77t, but then reduce it mod 13. 13 goes into 77 5 times, and you get 65. When you subtract, you have 12. So that is the use of the polynomial. And the polynomial must be irreducible. We looked at irreducible polynomials earlier on. So it must be, you must define a polynomial in your code. As I forgotten to mention that. You must define your polynomial. You must give your code the irreducible polynomial you'll be working with. Irreducible polynomial you'll be working with. So that your code is able, therefore, every time it multiplies, to reduce any power that goes beyond the embedding degree. So in our case, the embedding degree was 4. And therefore you can see it. You can see it there. So any power that goes beyond the embedding degree must be reduced. So you give your code that polynomial to do that. Now let me now show you how the code will be doing the inverse. That's what I want to do there. The question is, given this and given this, supposing I have this point, what is the inverse of this point? What is the inverse? This is a point. Not necessarily a point. This is an element of the. So supposing I have something like 7, 3. So I've just picked the first point, or this is the one I'm getting the inverse. I'm getting the inverse of that. But the good thing, it has polynomial form the way you wanted for security reasons. So how will this code be doing inverse? So once you know how the code will be doing inverse, you are now able to write the function that will be determining inverse. Then the same thing applies to this. This is still the inverse. I want to show, supposing I have this and I have this, can I show that this is the inverse of this using my code? The code should be able to verify so that it's not using a wrong inverse to do something. Then after that, after knowing how to write the code for doing inverse, I need to, suppose I'm given a point, x1, y1. Suppose I'm given this point. Can I get this gradient? And I want to double this point. This is just one point. I want to double it. So can I get the gradient? 3 x1 square plus a over 2y1. Can I get gradient? So I want again for us to know how to write this gradient. How to write this gradient that will be doing this. So when we do this, when we find a gradient here, you will then learn how to write it in your code. And then after getting this gradient, can you now find point doubling? Can you double this point? Can you double this point? So that's what we want. That's what we want to do. And after we've done that, look at the code and you see that how did we write the inverse for doing that, and how did we write the code, the function for doing slope, and how did we write the function for doing doubling. Now, so step one, we are finding the inverse. We find the inverse of this. So the code is supposed to understand what the code is supposed to, just before we do that, what the code is supposed to understand is that the inverse of this point is another point x, which when multiplied by this point, plus 5 t cubed, the result will be 1. So how do we find this x? Because x is the inverse of this, so that the product by this should be this. Now, so what you give your code is that the inverse x is supposed to be of the form constant plus bt plus bt square plus bt cubed. So that is how your inverse is supposed to look like. The inverse is supposed to be a point x, which is of this form. Supposed to be of this form. Remember, if it goes beyond x cubed, if it becomes x4, you reduce it back. If it goes x5, you reduce it back. So it's supposed to be of this form. So we are just doing this to take care of all possible scenarios, because we know that we are dealing with points that are polynomials here, and therefore the inverse of a polynomial would also be a polynomial. The inverse of a polynomial will also be a polynomial. So this polynomial is supposed to be a plus bt squared plus bt cubed. So we reach here because of the embedding degree 4. So you can see that then it's very interesting how we write the code that will be doing the inverse, because we must tell it how the inverse is supposed to look like, how x is supposed to look like. That is how x is supposed to look like. It's supposed to be, the inverse will also be a polynomial of that form. So that's what I've said here. I've said we want to find the inverse of this in this field, but we must understand that we are doing it by using irreducible polynomial that, and therefore that inverse will be of this form, where a, b, c, d are just constants. Now, so then, how do we find the inverse? How do we find the inverse? It is 10 plus 5t cubed multiplied by the inverse. We are assuming that this is the inverse, plus ct squared plus dt cubed, and this should give us the identity. One, two, three, four. 1, 2, 3, 4. This is our identity. Our identity is supposed to look like this. Under multiplication, we are multiplying. So our identity, again, when you're writing the code, your identity is 1, 0, 0, 0 under multiplication. But if you are adding, then your identity should be of this form. And addition. your identity. And we are doing this this is not just that. What is this? This is not just that. It is 0 plus 0t plus 0t square plus 0t cubed. So this is how the identity looks like. 0 plus 0t plus 0t square plus 0t cubed. This is identity and addition. Under multiplication, the identity is 1 plus 0t plus 0t square plus 0t cubed. So which I then just write like this. But then we must understand it how it is. It is 1 plus 0t plus 0t square plus 0t cubed. Now, at this point, just multiply normal multiplication. Let me just go to what I already multiplied, but this is what we are doing. So in my calculations, I avoided the zeros. I just wrote 1, but then I've said what it means, what the identity looks like. And what I've said it looks like is what you put in your code, 1, 0, 0, 0. And the other one you put 0, 0, 0. But in my calculation, I was just using 1, but you understand that is how it is. Now, when you expand, just multiply that, multiply that, multiply that, then that, you have 10a, 10bt, 10ct square, 10dt cubed. Then multiply this. You have 5at cubed. Then you have 5bt raised to 4. You have 5ct raised to 5. You have 5dt raised to 6 is equals to 1. That product is 1. Now, this power is 4. This one is more than 4. This one is more than 4. Using our polynomial, we reduce that power, and that is what I'm doing in our next step. So 10a remains, 10bt remains, the power is still less, 10ct square remains, 10dt cubed. Okay, I carried the other side, it's no problem. I'll show you how it came there. Then let me just put a star there, put a circle there. We've not used it. We've just picked this, picked that, picked this, and this one I put it on the right side, but let's wait. Now, so 5t cubed. I've also not put it. I'd forgotten, but then later on I put them. These two. Oh, no, I didn't forget. It's because of length, so I decided to factorize. It's because of length. You see, it was coming outside my page, so I decided to factorize. But now my interest is here. 5bt raised to 4. 5b, t raised to 4 is -2, which is 11. And t raised to 4 is -2, which is 11. That is why you can see 5b raised to 11. No, multiplied by 11. 5b raised multiplied by 11. And then here, it's 5c multiplied by 11. You see, t raised to 5 would be t raised to 4 times t. T raised to 4 times t. So t raised to 4 is this, 11. Then this times t. Then 5d t raised to 6. T raised to 6 is t raised to 4 times t raised to 2. But t raised to 4 is 11. T raised to 4 is 11. And then t square. Now the ones I skipped are 10 dt cubed plus 5at cubed. These ones I've just put them here. I decided to factorize t cubed outside to minimize on space because it was getting outside my page. And so when you factorize, what you get is what I've written there. Now, so we've reduced t raised to 4, t raised to 5, t raised to 6 using our irreducible polynomial. What then follows is to reduce the coefficients. Those that go beyond 13, we reduce them mod 13, as we've always done. So if the coefficient goes beyond 13, we'll then reduce it mod 13. Then reduce it mod 13. So the first three constants have not gone outside. So 10, 10, 10 have not gone outside, have not gone beyond 13. But this is 55. This is 55. Mod 13, 13 go there 4 times, because 4 times this will be 52. And the remainder will be 3. So 3b. The same thing happens to that, will be 3ct. And the same thing happens to that, will be 3dt squared. And this one I've just maintained them because they're different and their powers are still, or their coefficients are still small. The only thing they share is t cubed, but the rest are different. Now, so at this point, I remember that this is supposed to be this. At this point, I remember that. So when I remember that, and what do I remember again? I remember that this is a constant 1, and this is 0t, and this is 0t squared, and this is 0t cubed. So why I'm doing this is that I would then equate the like terms. Those without t, I equate them. So those without t, like for instance, 10a, and the other one that has no t is 3b. This one I equate to the one without t, the right-hand side. Then those with the t only, 10bt, 10b, and 3ct. I will equate it to 0. Let me remove t. I equate it to 0. So I'm just dropping the t's because they would then cancel out. There's no problem. They would cancel out. So those that have t, I'm done with those. So now let me come to those that have t square. I have 10c t square, and I have 3d t square. Then I have 0 on the right side. Okay, I'm done with those that have t square, those that have t. Now I'm coming those that have t cubed, and I just grouped them together. I was just waiting for this time. So 10d plus 5a t cubed, I equate it to 0. Now these are simultaneous equations that we then solve. And so how we solve it is how the code will be doing. Because the code will be doing this to get the inverse, the code is doing this is what the code is doing. This is what the code is doing to get the inverse. So the code is multiplying. First of all, you told it how the inverse is supposed to look like. A plus bt plus ct square plus dt square cubed. So it's multiplying this by whichever number you want the inverse. By whichever number you want the inverse, it's multiplied by that. And then expanding, after expanding, it's grouping this and then collecting like terms and equating those like terms. The ones on the left and the ones on the right. Then after that, now solving becomes very easy. Solving becomes very easy. If we could begin from here, for instance, let me look at this, for instance. This one means 10b is negative 3c. That's what it means. It's the same as, and remember this negative 3 mod 13. Negative 3 mod 13 is just 10. It's just 10. So this means 10b, let me write it here, 10b is 10c, which means that b is c. B is equals to c. What about this one? The same thing. 10c is equal to negative 3b, which means that 10c is 10b. No, this was D. This was D. This was D. This was D. So 10c is 10d, meaning that c is equals to d. So from these two equations, we can say that b will be equal to c will be equal to d from those two equations. So we have no problem with that. Once we get one of them, once we get b, we know that c is the same as b and d is the same as b. Now, the ones that are there, this one, let's come to this. This is the same as 10d is the same as negative 5a. Negative 5a, or you can say 10d is 8a. Is 8a. What about this? I want to deal with a first of all. So I can call this equation 2, and let me look at this. This is the same as 10a is 1 minus 3b, or 10a is 1 plus 10b. 10a is 1 plus 10b. Because negative 3 is the same as 10. Now, what is interesting about this equation 1 and equation 2? Look at equation 2. Look at equation 1. And look at this. So that means where there is b, we can write d. Because b equals to d, I'm referring to this equation 1 and I'm looking at it in conjunction with the equation 2. I want this to be b, 10b. So equation 2 can be written as 10b is equals to 8a. And this other one can be written as 10b is equals to 10a minus 1. I don't know whether you've seen what I've done. What I've done is 10b here is equals to 10a minus 1. 1 just calls the equal sign. You can write 1 or 12. 1 and 12, negative 1 and 12 is the same because we are working mod 13. We're working mod 13. Let me leave negative 1 there. So using elimination here, you can easily subtract this equation from these equations. When you subtract, this will be 0 is negative 2a plus 1. And this is just the same as, this is the same as 2a is 1. 2a is 1. So what is a? What is a? A is a half. A is a half. Mod 13. What is a half mod 13? What is a half mod 13? So we are asking ourselves, what is the inverse of? The inverse of 2. Mod 13, the inverse of 2 is 7. So A is 7. A is 7. So once you have A as 7, you can get B. You come back here and get B. Because A is 7, so what is B? 10B is 56. 8 times A, 8 times 10, 56. So what about B? B will be 56 over 10. 2 go here 28 times, and 2 go here 5. So you get the inverse of 5. The inverse of 5 mod 13 and multiply by 28. Then reduce mod 13. So all these workings I've done them. Let me just show you. But I was explaining so you understand what we are doing. And so once you do that, then you can write the code, and the code will be doing all these steps for you to get the inverse. So this is what I was doing. This is what I've been explaining. I've already explained this part. And then I've explained up to here. I've explained up to here, where we then now reverse. Where there is B, we can write D. And so we explain this. And then we now solve these two equations for A. Solve these two equations for A. And when you can arrive here, I'm just rearranging, but it's the same thing I've already explained, so that you get, we reached here where A was, 2A was a half, and A then became 7. And so from there, you now come and find D or B. In this case, I wanted to find D. Of course, D and B are the same. So then B becomes 8A, which is 56 over 10, which of course, when you do that, you get 28 out of 5. And this is bigger than 13. You can still reduce it, mod 13 to be 2. So 2 out of 5. But now you've given a code, a method of doing inverse, so that whenever you have 2 raised to some over something, you never have a denominator. The code is doing the inverse of this mod 13. So the inverse of 5 mod 13 is 8. So the code computes that and then says, therefore, D is 2 times this inverse, which is 16 mod 13. That will be 3. 16 mod 13 is 3. Now, so D is 3. And remember, B was C and was D. So D is 3. That means B will be 3 and C will be 3, but A was 7. And we had said that our inverse is supposed to be A plus BT plus CT square plus DT cubed. So that means, therefore, since A is 7 and B is 3 and C is 3 and D is 3, then our inverse is this. This is our inverse. The inverse for this code. That is how the code will be doing the inverse. Now, point doubling and point, okay, this is easier to do. I had shown it last time, where you given a point and it's inverse. Just to show that it's inverse, you multiply, and you want to see whether this product will be 1. Want to see whether this product is 1. So when you multiply, just doing that, getting this and that to be 48 t square, and this will be 4t raised to 4. But remember, once it becomes t raised to 4, you replace it by 11 or -2. And then this will be 132 t raised to 4, and that will be 11 t raised to 4. So you multiply those. When you multiply this, so what I was saying, the first one will be 48, reduce it mod 13, get 9, This other one would be 4t raised to 4, but t raised to 4 is 11 or -2. Oh, at this point, I've not reduced, I just left it, but I'll reduce it later. And then this will be 132 t raised to 4. So 132 mod 13 will be 2. 132 mod 13 will be 2. But then we'll come back and reduce t raised to 4. Then lastly, this will be t raised to 6, 11 t raised to 6, and it's there. Now combining them, I have this 9 t raised to 2, I have this 4 t raised to 4, I have this 2 t raised to 4, and I have this 11 t raised to 6. Now, our mission is to reduce anything t raised more than 4. Of course, this is 6. Let's just do that. T raised to 2 plus 6 t raised to 4, and plus 11 t raised to 6. Where there is t raised to 4, write -2. Where there is t raised by -2. So this would be 9t. Oh, I did not combine. I did it separately, then combined. But this is 4 times -2, which is -8. And this is 2 times -2, which is -4. And this one, I don't know why I did not do it at this point, but I did later. So I just wanted to explain that a t raised to 6 would then be this. And this second part, t raised to 4, is -2, 10 times t raised to 2. So t raised to 6 becomes that. Now multiply this by 11. Multiply that by, you get -22 t raised to 2. So this one becomes -22 t raised to 2. But -22 mod 13. If 9, then plus 13, that would be 4. 4t square. And there's another t square here, 9. 9, I just put it here. Just put it there, then reduced later. When you reduce later, it becomes 4. So 4 plus this gives you 13, t square, and there's this. But this one, mod 13 is 0. This one, mod 13 is 0. And -12 mod 13 is 1. So we've shown that those two numbers are inverses of each other. Okay, now let me show you the code because of time. Let me show you the code, and then what was very important here is how do you do the inverse? How to do the inverse was very important, and so wanted to know it. The code for Weil pairing is this. Now, I've noted that most parts are the same as the previous codes. I've imported these libraries, but I've said, of course, when you're dealing with the different pairing friendly curves, when you're dealing with the pairing friendly curves, then each one of them would require different libraries for you. So you would then import those libraries. I've defined my prime number here as 13. And I've also defined and said that wherever the power goes beyond 4, I would then replace by the modulo equivalent of 11. Because it's supposed to be t raised to 4 is -2, but -2 mod 13 is 11. So that 11 is the one I put here. So my code is now aware that every time the power would spill beyond 4, it will replace t raised to 4 by 11. Okay, so implementation of the point. In fact, I'm telling it the powers are supposed to be 0, 1, 2, 3. You can see I've said we are doing this from 0 to 4. So 0, 1, 2, 3. So every time I'm doing that, even for addition, I'm telling it to do the same thing. Whenever the power goes beyond, it should reduce. The power is always supposed to be between 0 and 0, 1, 2, 3. So this is why it's reducing. Function reduce mode t raised to 4. Function reduce mode t raised to 4. So every time t raised to 4 appears, it's supposed to be reduced by this function. Then the function for doing the inverse is here. And then there's function for doing powers. Function for doing powers. Now, those ones are common, but now the only thing that is different, look at this. This is for just doing point summation, doubling. If you're doubling, you remember if you're doubling, you must get what is that? The slope. And the slope is 3x squared. You can see 3x squared. So 3x squared is given by this x times x, then times 3. Look at the 3, how it looks like. The 3, for our case, the 3 is supposed to be constant 3 plus 0t plus 0t squared plus 0t cubed. So everything you're doing here, you must remember how the number it looks like. Then add a. Term a is supposed to be 8. It's 8 in our case. But now here, it's supposed to be 8 plus 0t plus 0t squared plus 0t cubed. Then the numerator is supposed to be 3x squared plus that constant a, which we've defined here. What about the denominator? The denominator is supposed to be 2y. So y times 2. But look at the 2. So I'm emphasizing how it's supposed to look like. And look at the identity here. The identity for addition. The identity for addition. 0 plus 0t, 0t squared, 0t cubed. Then after that, after you've gotten the lambda is here. Lambda is the numerator times the denominator, the inverse of the denominator. After that, you come and find x3 and y3. These ones we've always been doing them. Always be doing this. Now, the only thing again that is different is now the Miller's function. The Miller's function is this. The one that will be finding FR PQ and FR QP. So this is the Miller's function that is doing that. Then after doing the Miller's function, you have the Weil function, and then after that, you have the main function. So the main function I put the point that I put is Z72. This is a point, 72. But we don't just write 72. 72 is supposed to be 7 plus 0 t plus 0t squared plus 0t cubed. And then 2 is 2 plus 0t plus 0t squared plus 0t cubed. So that's point. That's the first point. P, coming from our group G1. Then from G2, we have point Q. And point Q is 7 plus 0t plus 9t squared plus 0t cubed. And then our y value, 0 plus 2t plus 0t squared plus 12t cubed. So when you now ask it to do Weil pairing for those points, it should do it. For just a minute. Just some minutes. Okay, let me do Weil pairing. Let me ask for Weil pairing again. Okay, so it has given me the Weil pairing for these 2 points. And this is what it has given me. While pairing, what you get, the result is not a point, but it's just an element. You get an element of that extended field. Get an element. So the element is 1 plus 9t plus 9t squared plus 4t cubed. So that's what this gives me. Okay, thank you. I just wanted to emphasize on how to write code, especially the inverses and so on. We have this part for finding a line function and so on. So I think we should stop there.